is going to be 1.2. The peak of the load is another 0.6. And then the other side over here is at 1.2 meters also. This is 1.8, my scale's not very good, and 1.2. So I've made it look like this triangular load is symmetrical. It's not. This distance is actually 1.8, and this distance is only 1.2. So the centroid is not going to be at the peak up here. Centroid is probably going to be a little bit to the left of that side. Now I could figure out where the centroid of that overall area is, but I don't even have to do that. What I can do is I can pretend that I've got two separate triangular loads. I've got one triangular load that goes from 0 to 2 kilonewtons per meter over a distance of 1.8. And then I've got a second triangular load that goes back from 2 down to 0 over a distance of 1.2 meters. So instead of treating it as one single distributed load, I can treat it as two distributed loads, both acting on the beam. I'll replace the first distributed load with a single equivalent concentrated acting through the centroid of the first triangle. I'll replace the second distributed load with a single equivalent concentrated load acting through the centroid of the second triangle. So R1, thinking of the first triangle as R1, the second triangle as R2. R1 is equal to single force equal to the area under the load distribution. It's a triangular load, so it's going to be 1/2 the base times the height of the triangle. So we have 1.8 meters, 2 kilonewtons per meter is going to give me a total force of 1.8 kilonewtons. Where does that force act? If I say the distance from the left end of the beam to where that single force is concentrated, it has to act through the centroid of the distributed load. Now, a triangle, the centroid of a triangle is 1/3 of the way from the base to the vertex. It's 2/3 of the way from the vertex to the base. So it's 1/3, 2/3, perpendicular distance between any flat side and the opposite corner. So A1 is going to be 2/3. I'm measuring from the point to the centroid, so it's going to be 2/3 of the 1.8, which is 1.2 meters. I'll do the same thing for the second load. Again, I'm going to replace this portion of the distributed load with a single equivalent concentrated load equal to the area under the load diagram, which is again 1/2 the base times the height. That's meters, kilonewtons per meter. So this is going to give me 1.2 kilonewtons. And the location of that concentrated load, this was A1. Now I'm looking for the distance A2, again measured from the left end. Well, I first have to go 1.8 meters to get to the edge of the triangle, and then the centroid is 1/3 of the way from the base to the opposite vertex. So I'm going to go 1.8 to get to the edge of the triangle, and then 1/3 of 1.2, giving me a total distance from the left end of 2.2 meters. Once I've done that, now I just have a beam which is acted on by 1, 2, 3, 4, 5, 6 forces. And I do my usual. I sum forces in the horizontal direction, which is going to give me RAX The distributed load is entirely vertical. The resultants of those portions are entirely vertical. The only other horizontal load is a portion of this 1.5 kilonewton, and the horizontal component of that is going to be 1.5 times the sine of 30 degrees, acts in the negative x direction. Summing forces vertically, I'm going to have RAY plus RBY minus the R1 and minus the R2. Sum of forces equals 0. If I take moments about the left end of the beam, well, that's not where I want. Sum of moments about A. Two of the unknown forces pass through A, so I'll take the sum of moments about A. The distance to the force B is going to be 1.2 plus 1.8 is 3, plus 1.2 is 4.2 plus another 0.6 is going to be 4.8. So it's 4.8 times RBY. And that force is going to give me a positive rotation around A. The constant